Welcome back. We will have the last lecture by Lorenzo on young needs in AdS4. And please, Lorenzo, take it away.
Thank you. So yeah, today, okay, as you might have noticed, I was much slower than my original plan, but I hope at least today to be able to tell you some things that we learned about this question. So let me remind you what the question was that we saw yesterday. So the question is, I want to study this theory in AdS4, not because I told you that I want to use the power of conformal symmetry of these boundary correlators to constrain a bit the behavior of my massive theories, in this case, means. And then when we put it in AdS, we gain this dimensionless combination, which is our new knob, which is a combination of the random generated scale with the radius. And then we know, or we believe we know, one is that, okay, certainly we know about this part, right? Because I can use perturbation theory. And I can study what are the possible boundary conditions for these free gluons that live in AdS. And two very natural possibilities are what we call Dirichlet boundary condition and non-boundary condition. And one crucial difference that here I have G global symmetry when I impose this boundary condition in my boundary correlation functions. In particular, I have some operator which is a non-abelian current conserved, which is protected dimension. Here instead, the G symmetry is gauged. Okay, so all the operators are singlets under G. So that's what I know on this hand. Then on the other hand, instead, I expect the theory to become like a gap theory of a bunch of globals, which are color singlets. So from the point of view of the conformal field theory of the boundary, this should mean that I only have singlet operators with dimensions that are growing linearly in the radius of AdS. Okay, so everything is very heavy. So it's immediately clear that this Dirichlet boundary condition should somehow disappear when we go to strong coupling. And the question is how to fill in here what happens in the center. Okay, and I want to say that this I like because it gives us a way to understand what happens to the naive picture of the Lagrange. The naive picture of the Lagrange is that we have gluons, and then by dialing this, we can understand how this disappears. In a sense, we see the moving of the onset of confinement, okay, as we approach flat space. And so one possibility is that this happens through what is called the marginal annihilation, okay, which means that there should be some other boundary condition, this star, Dirichlet star. So presumably this boundary condition is non-unitary coupling, but then it can flow to both of them. Okay, and this energy flow between this star and D becomes shorter and shorter as we approach some critical value of the coupling, and then the two boundary conditions merge and they become complex. So that's one very natural way. So this you can interpret as some kind of instability in AdS. Then another possibility is that, I mean, these possibilities are not really on the same level. They don't have the same explanatory power, but it's just various things that can happen in here in between. Okay, so one thing that can happen, which makes actually the picture a little bit more complicated, but we need to be open to it. It could be that actually the Dirichlet, some new line, if you wish, or boundary condition opens up, which is one which I have a kind of Higgs mechanism. Okay, so what this means that I have some relevant charged operator at some point from the D boundary condition, and using this charged relevant operator, I can flow to a boundary condition in which the symmetry is broken at the boundary. And in principle, since this theory now doesn't have the global symmetry anymore, I can also be open to the possibility that this new boundary condition, if it exists, is the one that gives me the singlet globals. Okay. And a third, more exotic possibility is that it could happen that just this boundary condition with gluons, it just becomes non-unitary at some point, meaning that the norm of the two gluon states, so this is the function of the current, contains parameter Cj, there's a central charge of global symmetry. This could continuously go to zero, meaning that the gluons become zero norm and they quotient them out. Okay, so this is the possibility that we saw. Questions about the recap? Okay, so now I want to tell you how one can try to test these possibilities. So first of all, what are the kind of sharp signatures at the level of the data of the CFT? Okay, here it's already phrased in terms of the data of the CFT. In fact, if anything, this is clear at the level of the data of the CFT. Is a little bit less clear from the point of view of the physics in the bulk. But okay, here we are saying something definite. We are saying that Cj is equal to 0. Now here, what are we saying at the level of the data of the CFT? Here we are saying that the B still has at some point above for some lambda, given some lambda, we call it H, okay, a relevant non-singlet operator. Okay, so perhaps I should specify that certainly we know that in the weakly coupled spectrum there is no such relevant operator because you can easily check. So the idea is that this can happen if at some point some operator crosses marginality and becomes relevant to non-singlet. Okay, this one instead, what does it say? It says that the signature is given from this operator that makes you flow from Dirichlet star to Dirichlet. Okay, so unlike this setup here, this operator needs to be a singlet. Okay, it's a singlet of color that connects these two boundary conditions and have the same global symmetry. Because only if it is a singlet, you can have this beta function behavior that gives you merger and annihilation. Okay, and then the signature here is that the D boundary condition has, or I mean, at some point has a marginal singlet operator. This is when it starts disappearing, okay, at this critical value for the larger configuration. Okay, so now these are questions that are phrased in CFT language, and I can try to see if they're realized. So one first thing you can do, which is the first thing we did, this was in a very collaboration with Marco Serrone, Ferdinando Cesare, and Riccardo Ciccone, is okay, at least we can try to test whether of this, which one of these things seem more reasonable from the point of view of perturbation theory. So computing how things deviate from the generalized theory spectrum. By the way, there is also another prediction that you have from this picture, which is that instead for Neumann, you don't expect anything to hit marginality, okay? But you expect actually dimensions to grow as you increase the radius, okay? I should specify that it's not like it's basically the generic thing that if an operator becomes marginal, the boundary condition will disappear, okay? And this happens because if you have a singlet marginal operator, there will be a beta function generated for it, and this beta function will have the typical merger annihilation behavior. Okay, so it's not that to like if you have a marginal operator, your boundary condition is doomed. Okay, so you don't want this to happen to Neumann if you want this to become the confined boundary condition. Okay, so the first thing we did is do some perturbative calculation. So let's see that what we did. So check. Of course, this is not going to prove anything, but depending on your case, you might find it to be a hint, an indication, nothing, you can choose. So what we did is that we took those the lightest singlet and non-singlet scalar operators in V. And also, since we're there, and the lightest in M. And compute scaling dimensions to perturbation field. Of course, I need to add the objective non-singlet in N, because in N everything is a singlet, because I'm getting values. Okay? Compute scaling dimensions. Perturbation theory. So what are these operators? Maybe as I say, the result, and then we also want to do how this operator to do. The results. So for D, the results of this. So delta S, by which I mean the lightest singlet, and then we call it sing for all this. So this lightest singlet starts with 4, okay, starts with dimension 4, and then it has a negative almost dimension, just this number. Which is squared. So this is we are doing perturbation theory in the Young-Mills coupling. You can think about it as the Young-Mills coupling at the scale of 1 over L. Okay, this is related, of course, to this problem that based on log. This operator is turns out to be the corresponding operator is just the trace of the AJ, you might imagine. Okay, so it traces the mu, or maybe called the index I, sorry. The boundary index is called phi. And you see the current in 3 dimensions is dimension 2, so it starts from 4, and then it has this negative one dimension. And crossing marginality, so the merger happens when delta is 3, okay? So you see that it starts also back from 3 and it goes negative. That's what perturbation theory tells you. If you compute the lightest non-singlet,
Wait, is this very analogous to flat space results? Or the...
I don't know, similar, what could be the analog of this result of flat space. Because if you want, the whole point in a sense is that you see it doesn't exist in flat space. But yeah, I guess in flat space you would still ask yourself, if you take the point of view that you have just gluons,
Yeah.
what is the energy of a two-gluon state? But there I wouldn't have some. See, here I have a clear parameter which to expand, which is in a sense the radius. There you would have to do it with some other energy scale. So yeah, this scale, what is the energy of the two-gluon state? Here I have a natural thing that tells me the scale, which is the radius AdS.
So you can always think of the flat space of the limit. So what happens if you take the limit of it?
Well, the thing that I want to propose is that if I try to take the flat space limit, it means increasing this G. Okay. So and then at some point this thing just becomes 3 and this thing becomes complex. Okay. There is an instability. So the leading non-singlet, which is the one that could bear all here, it's also negative, but it's a little bit smaller than this. It's smaller by a factor of 2. Okay. So here we are living a little bit dangerously if you want to know which one is reversed, but that's the cut. Okay. So this is the one that wants to go negative after perturbation theory.
But some of this is still analogous to the case in which you put the theory, say, on the lattice or on the box.
Right. Yes, you could do something similar by asking what is the energy of the gluon state in a small box.
Yes.
And then you take the box larger. Yes. If
I'm
you want
just wondering whether the technology of Witten diagrams here is, of course, is captured by this result, but at the end, the physical.
No, I agree. The physical question is similar to this one. It's just that, I mean, yeah, you're using more symmetric setup.
G is the Young-Mills coupling.
G is the Young-Mills coupling. Yeah. So this G, I mean, the Young-Mills coupling renormalized at scale 1 over L. Okay. Which is in one-to-one correspondence with this dimensionless thing that I said before.
But this result is quite universal, so shouldn't be the same whether you compute in flat space or
you're saying that this
the scheme dependence of G were which
well let me see. Okay, this thing at this order, I don't think is scheme. You see the scheme dependence of G. Of course, if you want, you can express everything in terms of just CFT data among each other, right? So if you want, you can express this as an expansion in 1 over Cj. If you want to be, you see what I'm saying? But okay.
I'm saying that, you know, if you match G at, I don't know, 1 over A scale, where A is the lattice spacing on some, you know, discretization, then it should be the same.
Okay, this I don't know. It could be yes. Bit.
I think the configuration is different, but probably I don't know the numbers, but
No, the condition to do is different, but if you take the same object you define it, to
I think if I have a big memory, it should be related to the Lusher potential. This
Sì, I think at all if you can compare to lattice level, it would be interesting.
But that was a question. I didn't know the a priori the answer. Yes.
Yeah, I mean, you can ask already how about this? How do you match this with some lattice? Like, is there some? I mean, this comes from the conserved current in CFT3, this 4, right? What is the analog of this 4 beyond the lattice? Not obvious to me, but.
But would you replace this by, so the usual people say that if you start from the conformal window, you start from the conformal point, then you have a current. Somehow you need a node, as you pointed out in one of the lectures.
Yes.
But in that case, that is the node.
Okay, you're saying if I start from QCD
Yeah.
from the top end of the conformal window.
Yeah, and then you might see what happens to a conserved current. No, sorry, no, this is yeah, this is the one.
But I mean, this I think. So that's like the current in the CFT that would be in the bulk. Like here, this you should think about it.
No, of course,
Taking
of course.
with like
Yeah,
some
yeah.
two gluon states.
Yeah.
Then the question is, if you want to compare to the lattice, what would you take with the energy of the two gluon state compared to what scale? To me, it's not obvious that you can reproduce precisely this thing, but maybe in some sense you can. I don't know. I just want to mention. Okay, so this non-singlet is the trace of it's the leading one is that happens to be the adjoint, which is I mean basically the ABC symbol with the two currents. Okay. So a fun thing is that this doesn't exist in SU2. So in SU2 actually the leading adjoint is heavier. It starts from 7. Okay. What about Neumann? In Neumann, you do the computation and find. So there's the likeness, let's say. Starts from 4, and it has exactly the same number with a plus. Okay. So in this case, the energy of this line state starts increasing. Okay. And the operator here is trace Fij F2J. So these two things, I mean, at least they are compatible with the picture of merger annihilation and continuity of Neumann, so that this thing doesn't seem to be going towards marginality, it seems to be going the other way, while this seems to be going towards marginality. Okay, then you can play dirty games like if you truncate here, how big you need to take G, but okay, that's not what just the picture, then going from a picture. That you have all of these things that starts from 4, you have marginality at 3, and well, just a picture of Neumann going up, and you have this singlet, Dirichlet singlet goes like this, and Dirichlet non-singlet goes like this. Okay.
Sorry, can you explain what's the consequence of it to go into marginality?
Yeah. So that was what before I erase, I was saying that if you want to have merger annihilation, okay, what merger annihilation tells you is that you remember there was this picture with Dirichlet and Dirichlet star, right? So and when it's to be this flow, it becomes shorter and shorter. So if you look at the leading irrelevant operator along this flow, right? So this is an irrelevant operator, irrelevant, always less and less irrelevant.
Mhm.
And then here it hits marginality.
Mhm.
Okay, so I'm just checking
Okay.
what happens to the lightest operator, and I'm seeing that indeed there is an operator that becomes less and less irrelevant. Okay, of course I'm not following it all the way. I'm just seeing how it starts behaving as I move away from perturbation theory, and that's what I get. Is it clear?
Yeah.
Okay. So maybe just I don't want to dwell too much on the perturbation theory, but we can compute this basically in two ways. One way is brute force with and diagram evaluation. And which is basically just say, you see these guys, all of them, they look like some double trace operator. I mean, I should say two particle operator in the GFF, the relativity theory. They contain this contain 2J and this contain 2F. No? So all of them are operators that when you insert them at the boundary, they spit out two blue ones. Okay. So the value for the leading order 4 comes from this diagram, and then we need to compute the leading diagrams for the correction. This is the 4, and then the order G squared comes from diagrams like this one and this one and this one. Okay, you sum the three of them and you get the result. Now, just one curiosity. One curiosity is that when we do these computations, there is one. So we did it using a covariant gauge because we wanted to have preserved the AdS isometries. To do it in covariant gauge, meaning these HeI gauges where you have the psi parameter of your propagator. So a curiosity is that if you choose a particular value, which is psi equal 3, the propagator simplifies a lot. Okay, so I just want to emphasize this in case in life you find yourself that you need to do computations. This study that people already studied in the literature of gauge theory flat space, and they observed that for this value there is improved behavior. And in this case, instead of a hypergeometric function, you find some much simpler function like some power of the rational function. Okay. Curiosity. There is also another way we can compute these things, which is a bit interesting. So I just want to mention it. And it also explains why you have all these 11s. Why there are these 11s everywhere. So you might remember one source of 11 in your midst, which is the best function to loop. And this is not a coincidence that we find all these 11s everywhere. The reason is that another conservative method. Another method to compute is, so if you think of your theory as selective of 3D ones, as so the limit of square to 0, then be formed by your mixed coupling. Okay, think about it in this way for a second. Then there is a special property when you put the CFT in AdS, which is the point that you can bifurcate it and obtain the setup called boundary conformal fit theory. Okay, what does this mean? So you start with this, right? Our usual metric, but up to the conformal factor. So when you have a conformal fit theory, the conformal fit theory doesn't see this factor, okay? R squared over D squared. So for all intents and purposes, when we put the CFT of free fluids in AdS, this CFT thinks that she is in flat space with a boundary, okay? So without any strange metric. Now, one thing that
Can you say that why does it become a value?
I'm just saying that if you put a CFT in AdS, so one property of CFT is that they only care about this conformal structure of the background. So the CFT will not see that there is L squared over D squared. Okay. And so the CFT will think that it's living in a flat space with a boundary. Okay. Now, in flat space, so when you have a BCFT, you might know that actually it was mentioned for defects in the seminar by Tekla, but there is a special operator which is called the displacement. Okay. And the displacement is a special operator that is tells you how the translations are broken in BCFT, right? There is this formula that is in the seminar by Tekla. And when you have this setup with BCFT, this guy has protected dimension. The dimension, which is always the same as the number of space-time dimension of the bulk. So in our setup, this will be a protected dimension of 4. Okay. So if you go and compute what is the displacement operator in the CFT of free gluon with non and Dirichlet boundary condition, you find exactly these two lightest operators that I mentioned before. Okay. So this D for Dirichlet turns out to be trace of JJ. And the D for Neumann turns out to be, sorry, I keep using different. Turns out to be trace Fij, Fij. Okay. So far we only explained the 4. Okay. But now the point is that so in order to predict that this guy's dimension 4, you use the bulk theory is a CFT, right? Now, what happens when you turn on G? When you turn on G, you violate this. Okay, so this is violated by G, but it's violated in a way that we control. In what way is violated? Here, instead of having 0, you have the beta function of your decoupling times basically trace over your bulk action, right? This is the formula when you have energy, the trace of T becomes a beta function. Okay, so this is now the thing that will force the operator not being protected anymore in a sense. You see, when the trace is 0, I mean a CFT, the bulk operator is protected. This beta function is precisely responsible for this operator not being protected anymore. Okay, so you can use this logic and relate the beta function to the Arono's dimension of this. Okay, so that's a simpler calculation, leads to a simpler calculation. Instead of computing these diagrams, you just need to compute something at 3 level. It's a kind of multiple recombination logic, and it gives you another way to compute these Arono's dimensions. Okay. I mean, I can give more detail on how this works, but questions?
Is this specific to AdS4?
No. This you can use in general. I mean, this formula that we derive for the so there is basically a formula that we derive that is kind of looks exact in the coupling. It's a formula between the scaling dimension of the operators that are the displacement of the UV CFT and the beta function. However, it also involves some boundary P coefficients. Those we do not compute except in perturbation theory. But it's easier to compute this boundary P coefficient than computing this beast. Okay, so the beta function we take from Peskin, we compute this boundary P coefficient at 3 level, and we get for free the scaling dimension of these two guys. Okay. Now, so the status so far is that we just saw that the perturbative calculation gives some hint towards the direction of the merger annihilation, okay, as being the correct scenario. Now I want to discuss, to conclude, another approach which is not perturbative.
So then the plus for the Neumann is just because in this mixing matrix you will have some negative.
Well, I mean, I don't have a smart, so when I compute this boundary P coefficient that I need, to fix completely the dimension. It turns out these don't have a strong explanation why, but it turns out that they come precisely opposite from normal distribution.
I was wondering if you somebody when you have we diagonalize the matrix to get the anomalous dimensions,
Yes.
but in general you would expect that one is positive, one is negative.
Yeah. No, I understand what you're saying, but these like they are not living in the same CFT. These two. It's like there are two different CFTs. But the calculation is very closely related, but it's not like they are two operators that mix. So this phenomenon of two operators that mix, maybe I can briefly mention because I'm not trying to discuss that. It will happen if you include matter. So if you include matter, you will have also in the UV a CFT of free matter, permeates, whatever you want. And then there's going to be another operator, which is the displacement of the matter fields. And then when you turn on the coupling, you need to solve a mixing problem. Okay. So if you do that, you will find that actually it gives you more confidence that this is not a coincidence, because when you add matter, you still find that with the Dirichlet boundary condition, you have two guys that go down in dimension, and with the non-boundary condition, you have two guys that go up. So it seems quite robust. Okay, now I will move to another approach, but maybe if there are other questions on the result before I move to the other approach. Okay. So another thing you can do, that you can try to use some non-perturbative method. And so we use the numerical conformal bootstrap. This we did together with many authors. And this was a big platform good was Marco Maineri, which you don't know, and people you know, Piazza, student of Cis, Marco Serone, and Vicky. Okay. So probably I covered it over. I'm the least expert of numerical bootstrap. So if you ask me complicated questions, I will tell you to send an email to Alessandro or Stefanos. But let me give you an idea. Okay. So what is this? Just a bit. Most of you probably know, but the idea is that you want to impose the crossing symmetry on the 4-point function, right? And you get a 4-point function of some operators. This is an expansion in conformal blocks with some positive coefficients, which are the OT coefficient squared. These are your conformal blocks. I'm being a bit more schematic because I think many of you know. Okay, and then you impose crossing symmetry. Okay, crossing symmetry takes the form of. So what do I mean crossing symmetry? So this, for instance, you did the OP in one channel. Okay, you get the conformal blocks in some particular channel with the operator set there. And but then the same 4-point function you can rewrite by doing the OP in a different channel. And this gives you some constraints. This form, there are some functions here that depend on the primary operator exchange, which is basically the difference between the conformal block in one channel and the conformal block in the other channel factors. Now, so you have to put some normalizations, of course. And the sum is all the identical here and the O of E. Now, what do we do with the numerical bootstrap? You find that there is this approach which is dual, that we have from as matrix bootstrap lectures. The approach consists in finding some functionals that you use to hit. Oh, sorry, zero. You find some linear functionals that hit this operation, okay? And you try to impose some. These functionals give you some, for instance, positive number for most of these functions. And thanks to that, thanks to the functional give you some positive number here, thanks to the fact that these OP coefficients squared are positive, you manage to get some constraints from these equations. Okay? Like, let me give you a concrete example, which is the one I'm going to use. So suppose you want to get you want to objective. Your objective is to get a constraint on some of the coefficients. This is going to be relevant to my example, so that's why I'm reviewing it. Suppose you want to get a constraint of the coefficient. How do you do that? So let's you isolate from this equation the operator that you want, whose of the coefficient you want to constrain. Okay. So this equation becomes something like there is the contribution of the identity, and then there is some of the coefficient of some particular operator that you want to constrain. Okay, and there is all the rest. Let's say for different from this delta star that you want to isolate. Okay. Oops. And this is your equation. So how do you put bounds on this optic coefficient? What you do is that you look for a functional with the property that sorry, you normalize it basically from the action on the f of the operator that you want to isolate. It's just a normalization of your functional, and then you require that this quantity is positive for all of these contributions here. Okay, suppose you do that. Then if you manage to find numerically a function that does this, so this numerically the way constructed is from derivative of functions at the crossing symmetric point. So if you manage to find such a function, then you see here you have just a bunch of positive stuff, takes unitarity. Here you get 1, which multiplies your optic coefficient. And so you get a beautiful inequality, which is that this quantity must be smaller than minus alpha applied to the identity. Okay, so that's the way it works. So it was a very fast review, just because I want to tell you some idea of how it works in our example. Questions about this? Okay.
Maybe some question, maybe we're interested to the next. How do you find such an alpha?
So yeah, the way this is done numerically is that you explicitly know these functions, what they are, and then you build, you turn them, instead of doing infinite dimensions because it's too difficult, you turn them into big vectors by taking derivatives at some particular point, at a symmetric point, and then it becomes a problem of optimization that there are algorithms to solve it. Basically, now find some matrix that has some these big vectors with these properties. Okay, so now in our particular case, how do we apply these ideas to emits in AdS? So we want to see something about the Dirichlet boundary condition, okay? And in the Dirichlet boundary condition, there is very universal object that we know exists, which is this current, right? The non-abelian current. So we're going to take our operator now, which will was the symmetry constraint, to be the non-abelian observed current. We apply to HeI. And so of course the cartoon that I told you, I didn't include indices. Here there are a lot of indices. There is both spins and there is also indices of color. Okay, so this makes it a little bit involved technically. But in particular, so we impose the crossing symmetry constraint in this, and in particular, I want to mention that there is one interesting exchange to this four-point function, which actually tells you the leading deviation from the generalized theory. So here there is an exchange of J, we call it limits M and E. Okay, so this current itself is exchanged here because this is the statement that the non-abelian current is charged under the symmetry. And the optical coefficient, so there are two structures. Okay, because of the index, it's actually not like a scalar case, which you have just one block with one coefficient. Here it turns out that due to the indices, you actually have two structures that you need to take into account. And in this section, there are two structures in which there is one coefficient. You can think about it as 1 over square root of Cj, okay, in the normalization in which the current is uniquely normalized. But there is another one, if you want an orthogonal combination, which we call alpha JJJ, okay, not very illuminating. But what I want to say is that this kind of not fixed, so it's the contribution of this coefficient, we choose it in such a way that this was it doesn't contribute to the world identity, okay? So the contribution of the world identity is universally fixed in terms of this, but then there is an additional coefficient that appears. Okay. And this means we can, if you want to compute perturbative, and you find that this perturbation theory starts from some value of 3/4 plus some order t squared. Okay. Just to mention that you know what it is. When you have computing power. So now you see what I want to do is that I want to use this technology that I just reviewed of bounds on P coefficients. So with the appropriate tweaks taking into account of indices, I can use the same logic here to give you a constraint on this object, okay? 1 over Cj. So there is a problem, and the problem is that there is additional alpha. But what you can do is that you can repeat this algorithm for scanning, let's say, the values of alpha. Okay? So for each value of alpha, you can go and apply this OP coefficient bound, and this is going to give you a bound on Cj. And so if you remember that the bound of the coefficient squared was that it was smaller than some amount. That was the form of the bound. So this is going to tell you that 1 over Cj, in our case, is going to tell you that 1 over Cj is more than something, or equivalently that Cj must be bigger than something. Okay. So let me show you the result of the numerical analysis. Maybe at this point I can break down the.
Can I ask?
Yes.
Can you repeat what was with the one coefficient in the alpha JJ? What was the alpha JJ?
Well, okay, I'm just saying that there are two structures and you can choose the basis. It's actually that one structure is the one that is universally fixed by the world identity. So there's just, if you want, the charge of the current divided by square root of Cj. And the other structure, which has this coefficient alpha JJ, it goes away when you doesn't contribute to the world identity. Okay, so that's the choice of the general structure. Okay, so let me jump to that.
Automatically, once you fix the first one, the second one will not appear over there.
Well, I mean, you could, if you put here the correct coefficient, yes. I mean, you could have, yeah, so this structure. Yeah, okay. So here, I mean, those of you that are familiar with this, I mean, you see, this is the what before I told you that we fixed one how the functional acts on the interesting operator. In this case, the interesting operator is the block of J itself. So this is the normalization. And then object, this is terminology, objective, blah, 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 is because you see that my bound was how the functional was acting on the identity. So in this sense, this is the objective. Okay. And all the other things, on all the other operators, I'm imposing my functional is positive. And let me show you the figure. This is the figure. So you see we're scanning over the other guy, and we get this bounds. And I mean, it's not so important the detail of this result, but what is important is that, so this is for SU2 Young means, and this is for SU3. The important thing is that you see very clearly that the constraint of crossing symmetry and unitarity tells you that there is a gap above 0 for this CJ. Okay, so this rigorously rules out the possibility that as you increase your radius for AdS, the parameter CJ continuously reaches 0. Okay, so that's a nice result. That's non-perturbative that possibility is ruled out. Okay. Now I can tell you something instead about the dimensions of the singlet and singlet operators. So how much time do I have?
We started the 10 minutes.
Okay, okay, so there is still some time. So maybe I can maybe write something here. But the first conclusion we get from this non-perturbable analysis is that this decoupling scenario cannot possibly happen. Now, what about instead the dimension of the, remember we discussed before the dimension of the singlet and its singlet, and we can try to put some bounds here, right? So another thing you can do with the similar techniques like with these functionals. So we saw before I showed you a cartoon of how to put bounds on the pivot field, but you can also try to put bounds on the lowest dimension of operators appearing in the in this of P, right? So now you can say, okay, let me isolate from this sum of all the exchanges. Let me isolate, I can isolate the
polygon case because so
yes,
this is for a fixed SC1 theory.
right.
Do you know if time grows large, what happens to this?
How it moves as a function of n? Unfortunately, I don't have a good sense of that. I mean, we only did it for SU2 and SU3. Oh no, because I don't want this is true. I'm wrong. The one with the yes, so we got it. So I got about it.
As you know, it stays
Yes. So this is the alpha J star is the value which is meaningless. Okay. So got all this. So yeah, the next thing we want to do is that we want to isolate the contribution of the singlet to the lowest dimension of the singlet and non-singlet. Okay, so the non-singlet. Now, depending on the gauge theory, depending on the gauge group, we might have slightly different representations appearing. Okay, so you need to look at what are all the possible products of adjoint and adjoint. Okay, and in the cases of we focus on the cases of SU2 and SU3, and it's the most interesting case. The one of you remember before I told you that this dimension 4 minus something, okay, and that thing, this particular operator does not exist for SU2 because of the DABC symbol that does not exist. So in a sense, it's slightly more interesting to study this problem for SU3. Okay. Instead, the lightest non-singlet that exists for SU2, it happens to have a positive anomalous dimension, so it's 4 plus something. Okay. The adjoint starts from dimension 7. There is another representation that appears here, which starts from dimension 4, but it's 4 plus something in the equation theory. So it's less interesting, less heating. Now, here we do various things. So now this becomes a little bit more technical because you need to put some assumptions in order to have some sensible results. And let me explain what are some explorations that we did. So the first possibility is that we don't put basically any gap assumption. So you just assume the lowest possible assumption, so unitarity, crossing symmetry, and else. And then, sorry, And then what you get is something that is not very constrained. Okay. So if you don't do anything, you find something that is pretty not illuminating. You just find these things. So these are the dimensions of, for instance, the singlet, and is the name of the representation for the non-singlet. And the dot is generalized free theory. Okay. So by itself, this doesn't tell you much. Generalized free theory is still inside. And if you don't put any gap assumption, you just find these square regions. Okay. Now, you can play the opposite game of putting very strong assumptions just to test if things changes. And if you put very strong assumptions, you find that with not so many derivatives. So what are the strong assumptions here? We basically put that all the dimensions must be generalized free theory or above, for instance. Okay. So if you put generalized free theory or above, indeed you get an island that shrinks on generalized free theory. Okay. So this gives you some hope that you can play and find something. So no assumption gives you nothing, and very strong assumption gives you the island. So maybe with some assumptions, you need to play with the gaps, but you can hope to find something interesting. No, okay. Moderate assumption means that we just impose some gap which is between unitary bound and GFF. But here you start seeing something that is already a little bit interesting, like this for SU3, where I told you that there is the adjoint and the singlet. What you see is that see before with very strong adjusted an island around generalized free theory. Now when we do this, you see that immediately it seems like he wants to allow the singlet to have a low dimension and not so much the adjoint. Okay. So remember that the motivation here is to test which one between the singlet and the non-singlet will is more likely to cross marginality. Okay, because if the adjoint crosses marginality, we have the higgsing scenario. Okay, if the singlet hits marginality, if we could prove that instead the singlet becomes marginal first, this would be in a sense a proof of merger annihilation. So that's the motivation for this kind of plots. And here you see that indeed you see this region opens, which allows the singlet to be below 3, and it seems that the allowed region is more asymmetrical and reverse the singlet to be marginal. Now, we need at this point to do something a little bit more aggressive, and what I want to transmit here is that the difficult thing in this game is that we are really trying to target a family of theories, right? Because you have a continuous family, which depends on this knob. And it's also clear how to input this continuous parameter when you do this type of numerical bootstrap, right? We don't have a way to input L in our theory. So we had this idea of trying to do it by playing with the gaps. Okay, so it's what we call train to the floor. So the idea is that you start with you use this parameter delta, which is a gap around the value of the generalized free theory. Okay, so the idea is that when you're extremely covered, you're going to have generalized free theory, and then you move your gap assumptions to this parameter delta around the windows of generalized free theory, and this delta then plays like the role that it plays is like a proxy to the decoupling. Okay. Now, okay, there are some details of exactly how we put these bounds. We use some scaling with spin inspired by Lightcon results, but these are more technicalities. Okay, so the idea is to use this delta, which plays a role of, and we only put these bounds like windows of gap in the lightest operator to each family. Okay, and then for the other ones we are just using bounds. So let me show you what are the results with this tracing the flow. So, okay, I think it's more interesting to look at SO3, but okay, it's important to do that indeed the singlet, so the leading non-singlet representation is this SS bar, and you see that the singlet, the minimum value was possible for the singlet. Process marginality before the singlet. Okay. let me show you first the definition of S3 because it's important. Okay, so here for S3 you have again that the singlet wants to become marginal before the rotations. And yeah, so these are features for in the plane where we have the dimension of the singlet and the dimension of the joint. And these rectangles are regions obtained by extremizing separately the two dimensions. Okay, so you see that as you increase delta, this region wants to increase much more in the region of delta singlet becoming marginal before the joint one. Okay, and this line here is perturbation theory. And this, if you compare with some other representation, which you see that perturbation theory in this case gives it positive anomalous dimension, so in a sense it's less interesting, but it's still giving. So the most interesting constraint comes in here, this picture, because both they are joined in the singlet and negative anomalous dimension, so we want to test. Okay, so these are basically the results on the dimension of operators inside. Now, these results, in case it's not clear, I should stress that they don't prove rigorously anything, right? Because here we have a big allowed region, and we have no idea where Young-Mills sits in this big allowed region, okay? So the fact that the boundary, so the extremization was to push more in the direction of the singlet becoming marginal, that doesn't tell us anything because we don't know that Young-Mills lives at the edge, this bound, okay? But it could be that Young-Mills is here, and then it crosses marginality for the joint before. But it just, we find it as a suggestive hint that perhaps this is what's happening. Okay, so perhaps the singlet only becomes actually first. That's the best we can do.
I think that we should do already stuff like this, then it models actually some level of crossing.
Level crossing can happen because there's different representations, right? So they don't care about each other. So yes, I leave it to you to judge how much this adds to perturbation theory, but both of them don't give us a conclusive answer. So I guess for the future, like the big question is, what would it take to try to really isolate some island in these Young-Mills, and then rigorously prove that it crosses first in this direction? This would tell us, okay, this is the way the confinement transition happens. We won't get there. I should also mention just briefly that there is another non-perturbative technique that is this ODs developed. So in principle, so at the moment this technique only exists in 2 dimensions, and it's a technique in which one writes some differential equations from the data as a function of the node, as a function of this dimensionless parameter. At the moment, we don't know how to do it in 4 dimensions, but in the future we hope to try to apply as another non-perturbative method. It's independent logically from the confinement structure. Another method that will future users try to use. Yeah, I think let's stop here.
Okay, thank you, Lorenzo. So we can have questions.
If you are looking for correlators, you expect to get an island or?
I mean, in principle, yes, but yeah, the point is that this like 4 point of spin 1 on a million, I think what I understand from my expert collaborators, it's a bit at the edge of what people can do. Like here, you know, also we need to scan over many parameters. We need to scan over this flow parameter delta, and we need to scan over alpha JJJ. And so this requires the use of all these techniques to navigate or sort of heavy. So maybe in the future we will, I mean, technology will improve and we will be able to do also multiple correlators and get islands. It would be great, yes.
Can we go back to the method of with the displacement operator?
Yeah, sure. I will give you a lot of details for that, and more if you want.
Yeah, I was thinking about that line that you drew with the G hat, so G and Mills times L,
Yeah,
and a dual description, but instead of turning on the couplings of G starting at 0 with the CFT of 3 gluons, if you instead thinking, one could think of a very small sized box.
Mhm.
And so the way I was thinking is you have some region, you're doing a dilatation, and the first thing, you have a CFT, and as you're going away
Yeah.
from that region, the first thing you see is the AdS scale. So you have a CFT and AdS, which
yes.
it's becomes that. And all of that can be done at finite coupling. It's just a hierarchy
I'm gonna,
of the L and G.
you're saying if G
Is much bigger
is
than
the scale of set by the mixed coupling is much larger than the radius.
yes, and
Yeah, so this means that you're in the small radius setup.
yes, that's
Yeah,
my
then
question.
then you can use perturbation theory. I
And
mean,
is it and my question is it the same thing here? So
Yeah, that's
this
basically
effect where the better function appears?
yeah, that's basically what we're doing. I mean, this setup is the one in which you use perturbation theory. You can, but I don't know how to resign. If you're hinting that perhaps you can get exact answers, this I don't think is. I mean, it's
No,
exact in
I-
the sense that perturbation theory is valid, so I can.
But the thing that becomes less clear to me is how the beta function appears then, because you're always very.
The beta function appears because it gives the leading way in which the theory realizes that it's VDS. Like when you are at in the free point, let's say, in a sense, you lose memory of the background because the theory becomes conformal.
Yes.
Okay. So that's what I'm saying. So the leading deviation from this conformality is controlled by the beta function in the bulk. But we can remind your question.
It's just because in the small box limit, GM Mills is non-zero. So the trace anomaly is always there, right?
I agree, yes.
But I guess it's controlled by the.
Maybe one thing that I should mention, which is a bit peculiar, is that when you study quantum filtering in AdS, there is no enhancement of symmetry if you have a 1, 2, 15 with mass or if you have a CFT in the bar. Symmetry is still the same because the somebody doesn't care about that. So the thing that changes, as far as I know, is just that whether you have a displacement operator at the boundary or not. So really the signature of the fact that your bulk is becoming conformal is that you have this protected operator that basically controls moving the bulk, the boundary a little bit. Okay. So whether you have or not have this protected operator tells you whether you have conformal symmetry deep in the bulk. But other than that, the actual symmetry of your space doesn't change at all. So until,
Can you say something about QCD? What's the status of this kind of research for master's QCD, for example?
yeah, for master's QCD, the status at the moment we don't have some numerical bootstrap, nobody did it. The status is that we did the same perturbative checks, and it works similarly in the sense that the Dirichlet boundary condition that it seems like it wants to go towards marginality, meaning the singlet operator is reaching 3, while for Neumann the dimensions seem to be increasing. And that's one thing that we know for QCD, and there is an interesting story there also about what boundary conditions impose on the matter, poses to the fermions, right? Then a cool aspect is that even at weak coupling, you see a condensate, okay? So the scale of the condensate is given by the radius of AdS instead of being given by lambda QCD. But then there should be some way that this interpolates as you take the radius to be large, interpolates to the that space condensate. And another thing that is a bit strange, if you wish, that you can have many different boundary conditions that break the current symmetry in different patterns. So there is a bit of a similar story there of seeing more possibilities of decoupling than the ones that are realized as uncoupling, similar to there is a question there of out of all the possible patterns, but that's only one survive specifically. So interesting question that is not being answered. I didn't have time to mention there is interesting work also with the normal boundary condition by his collaborators, which they study the flux field. That's also good stuff.
Okay, let's thank Lorenzo. Okay, we now go upstairs that we have the lunch break. Just a small change in the afternoon schedule. We will resume at 1:45. Okay, and with the lecture of Andrea on the S matrix bootstrap. This is just to adjust some constraints of the second speaker, which should be Alexei.